This video is a lesson for the honors class on some additional bonding material. The first additional topic to discuss is called resonance. Resonance has been mentioned in class, but essentially what it is when you can draw a Lewis structure covalently in more than one acceptable way. Certain examples are things like CO3, which we've drawn in class to look like this, where the two oxygens on the bottom contain a -1 formal charge. So overall, this ion has a -2 formal charge. However, I can redraw this differently as putting the double bond, say, over here instead. I'm really just rotating the double bond around, and it will still have a -2 formal charge. These two structures are identical, but since we can draw them differently, we say that they are resonance structures. So whenever you can draw two or more versions of the same structure, that's correct, you will have what's called resonance. Another advanced topic is called coordinate covalent bonding. This occurs when lone pairs on one atom are used to make a temporary bond. It's not a full covalent bond, but they all come from one atom. They're not one from each. They're two coming from one side. The one that's coming in to bond actually doesn't contribute any electrons. An example of this is when you have a compound like ammonia, which we've drawn before, and it looks like this. And this is just a normal structure, right? No issues with this. But let's say another hydrogen ion were to come in and try to bond. This hydrogen ion doesn't have any electrons to share. However, it will pick up on the lone pair that nitrogen already has, because remember, two electrons are used to form a bond. It really doesn't matter if the two are coming from this one or one from each. So if nitrogen is contributing two altogether, he can still bond temporarily with this hydrogen. So what we have is the ammonia structure, and then this hydrogen is just sitting on top. We don't draw it as a line because it's not a full covalent bond. It's a coordinate covalent bond. The hydrogen is being attracted because of these electrons, but it's not really stuck to this nitrogen. When anything were to break here, it would be this hydrogen would be the first one to come off. This also occurs in water. Here is your general structure for water, which you've known how to draw, and it has two sets of lone pairs. A hydrogen ion can come along and try to attach itself here and make a coordinate covalent bond. This makes something called hydronium, H3O+. And what that really is just water with another hydrogen on it. It's an acidic hydrogen. This forms an acid in solution. These are examples of coordinate covalent bonds. The next advanced topic is called molecular hybridization. Hybridization is when orbitals and atoms combine with each other in a compound and make what's called hybrid orbitals. In previous lessons, we learned about S's and P's, S orbitals and P orbitals, and those were for individual atoms. However, when atoms come together and make bonds, we can make hybrid orbitals such as sp or sp2 and so on. For example, in the compound CH4, we have the C's and H's all connected by covalent bonds. But if we were to dig deeper and see where those bonds actually came from, remember that the hydrogen only has s orbitals in it because it only has one valence electron. But the 4 valence electrons for carbon encompass s and p orbitals if you look at your periodic table. So if we want to know what the orbital is for this exact bond, it's a hybrid of s's and p's coming together. We actually call this one sp3 hybridization. And on the next slide, I'll show you how I got that number. It's actually a really simple calculation that you have to do. What you do with your compound is you count the number of atoms attached to the atom you're looking at. Usually that's the center atom. So for example, again, that carbon in the middle of CH4. If we want to see how many atoms are attached to it, in this case there are 4 atoms, 4 H's around it. And we say don't count the bonds because if there were a double bond somewhere in this compound, if it was not hydrogen, you wouldn't count that twice. That would still count as just one type of bond. The same goes for a triple. That doesn't count as three bonds, it's really just one other thing attached. So count the number of atoms attached, and then count the number of lone pairs that are on the atom, not the individual electrons. So you want either one pair, two pair, or three pair. And you add those numbers together. So for this carbon, there are four things attached to it, and there are no lone pairs on it. So it's a total of four. That means the hybridization is going to be sp3 hybridization. And what that means is there's one s and three p orbitals. And when you add one s and three p's, 1 plus 3 adds up to 4. And we could have various hybridizations all the way up to D2sp3. And again, if you were to just count that, there would be 2 plus 1 plus 3, which adds up to 6. Here are some examples. Pause the video at various points to determine the hybridization of the element being asked. For our first example, let's look at the nitrogen within the ammonia compound. Pause the video here and find the hybridization of just the nitrogen. As you count this up, you'll notice there are 3 bonds on it, 3 atoms attached, and 1 lone pair. So altogether that adds up to 4. So the hybridization of the nitrogen would still be sp3. Even though there aren't 4 bonds to it, the lone pair does count. And again, we are counting the lone pair as just one. It's a pair. We're not counting the individual electrons. Now pause the video and try to find the hybridization of just the hydrogen in this compound. When you look at the hydrogen, you'll notice there's just 1 bond on it and no lone pairs. So the hybridization of hydrogen in every compound is just an s hybridization. Hydrogen cannot take on any p orbitals at all. For our next example, let's look at the carbon, either carbon, in this compound over here. Pause the video and determine the hybridization of this. When you figure this one out, you'll see that there are 3 bonds, 3 groups to it. Again, the double bond is not 2 bonds. We count it as 1 group hanging off of the carbon. So there are 3 things hanging off here. So this would be sp2 hybridization. 1 plus 2 adds up to 3. This would be symmetrical with this carbon, and then all these hydrogens again would still be in S configuration. Lastly, look at the sulfur in sulfur hexafluoride and determine the hybridization of this sulfur only. Pause the video here. When you count this up, you'll notice that there are 6 groups hanging off of the sulfur, 6 atoms, no lone pairs. This is our largest hybridization and would be D2sp3. You may also write it as sp3d2. It depends on what textbook you read on the ordering, but either one is acceptable, as long as it adds up to 6 numbers total.